angles unless you do a proper measurement, or whatever are the limitations of the fan, you won't be able to get the maximum out of it. That's basically because of this drag component that we have discussed, and based on this particular fan laws that are used for designs. This we've already talked about. The fan performance obviously depends on the size, shape and speed of the impeller, and it is essential to get the proper desired airflow and system pressure. You will have to go into this. For any fan that you want to check, we talk in terms of fan characteristic curve. Without this characteristic curve, you won't be able to really choose the proper fan for your application. So most of the people give these curves, but then finally at the end when you're in the plant, you're not able to measure some of the things like static pressure, because in situ measurement of static pressure is so very difficult. What you can do in situ is maximum somewhat accurately within the permissible inaccuracies of field measurements, the airflow pattern or airflow from the fan. That's the best you can do out of these. So the curves would generally give you an idea, and these curves are drawn for various blade angles. This is a simple curve which we had given for a particular blade angle. So like this, various curves can be generated for various tip angles that you use at these fans. These are all formula which I use. Obviously without theory there is no practice, so but we will not go into those details. We've already talked about it. We have achieved in fan coolers higher airflow. We have seen that with better design systems, there are lower vibrations and low noise and lower power consumption. Some of the specific cases that we have seen I would like to mention is when we've given them the fans for increasing the airflow, the thrust that is achieved by our fans was so much better to give them the higher airflow, but the structure which supported these fans could not take the higher thrust. And so we had to limit the blade angles of our fans to achieve a proper combination of the airflow improvement and structural stability. These are in some cases that have happened. I said already why hollow FRP and composite material. I think we have discussed this already. Our blades are all made of FRP, fiberglass reinforced plastic. We can use different resins called vinyl esters or epoxy resins, and they can continuously expose to 160 to 180 degrees Celsius. We are talking of the radiant heat that comes out of the spring tubes. We are not talking of the effluent that is going in the tubes. That may be at 230 or 240 degrees, but finally the heat that is seen by the blades is of the order of 120 to 150 degrees Celsius. Maximum, even if one fan is off, it can be seen to that. We can specifically give now, recently we have done some work to go up to about 200 degrees Celsius continuous exposure. The center bush, which gets onto the fan shaft, is made of cast iron. The hub plates, we have been giving even stainless steel 304 or stainless steel 316, depending on their requirement in the environment for corrosion purposes. The clamps usually are given aluminum alloy, LM6 or cast iron. The hardware, as a design choice, we give them all SS304 stainless steel. Well, this I think sums up all. Optimal aerodynamic design of impellers to provide higher efficiency for any specific application. The reduction in overall weight of the fan. This is one aspect which I just want to touch upon for a minute or so. People think the energy conservation is possible because the weight of the blade is less. In fact, the weight of the blade has got no relevance in trying to have the overall energy conservation or reduction in the power. Okay? That happens, why? It's only the starting torque of the motor that is required to be overcome depending on what is the GD square or the moment of inertia, which is finally related to the mass of the equipment that you want to drive. So it's just that starting torque that will be required less in a hollow FRP plate design or higher torque on a metallic plate. But it is the operating torque, which we are talking in terms of operating power, which is basically because of the superior aerodynamic design that there is an energy conservation possible. The general thought is, oh, the blades are lighter and so there is an energy saving. No, that's what I just want to clarify in case some of you had to say this. Basically what it does is, the life of the mechanical systems, the drive bearings, everything, they have a higher life because you are using a lesser load on them. They require lower drive motor rating and light duty bearing system, low power consumption, appreciable energy savings, compression molding technique we use, resin transfer molding technique, so that they have consistent quality and uniform dimensions. The aerofoils that I use would facilitate low flow noise and mechanical noise level compared to conventional metallic fans, longer life due to improved mechanical strength. About the resin, it's a design concept, but if any